Welcome to one of the penultimate sessions at Java 1, Vectors for Java. I'm Paul Sandoz. I work for Oracle on the JDK, on core libraries and the language bit of hotspot. And?
I'm Ian Graves. I work at Intel, and I'm helping Paul out on the Vector API.
I'd say vice versa. And there's also Vladimir Ivanov, who unfortunately can't attend us today, who's doing some really cool hacking in hotspot and is saving us and getting good performance numbers out of hotspot. So just to make sure, if you think this talk is about Java Util Vector, you are in the wrong room or perhaps in the wrong decade, or both. But there may be a talk where Vector is actually relevant, and that is a deprecation talk, maybe in the future. Who would like to see Vector deprecated? It's harder than you think.
It has its uses.
It does. It does indeed. So here's a safe harbor statement from Intel. I will just gloss over this and the next page. Oracle's is shorter. That's all I will say. Basically, you can't trust each other.
Nope.
Okay, so this presentation is about the design of high-level Java APIs and their implementations that leverage modern hardware for high-performance data processing. When I wrote that slide, I thought, maybe I should join marketing, because that almost says absolutely nothing. So then I said, more specifically, we want to design some experimental APIs and their implementations that can leverage SIMD instructions on modern CPUs. Everyone know what SIMD style instructions are? Yes, good. So that's the essence of what we're going to talk about. So in the overview, I'm going to start out with some very simple examples, and then we'll slowly build up and get more and more complex and say what we're doing in the experiments and say how they're working out and where we're going to go forward. So it's going to start really simple and slow and exponentially, rapidly sort of shoot off as Ian starts talking. At the end of it, we'll have cats with propellers on us, all going crazy. Okay. So going parallel. I've talked about going parallel many times before at Java 1 with streams, so forth like that, but you can go parallel at the machine level. We've all seen that done with Hadoop, MapReduce, and Apache Spark. Clusters, massive clusters of machines going parallel. You can go parallel at cores of hardware threads like Java Stream API and the fork join API. And you can even do it at the level of CPU instructions and coprocessors attached to them. And you can leverage this at each stage if you want. So Java streams, you can even use Stream-like APIs to do sort of parallel level at the machine or cluster level, like we've seen with coherence and think InfiniSpan as well. And you can even use Stream-like computations to leverage CPU instructions, and we'll show some of those going forward. So on CPU instructions or coprocessors, most modern chips now support SIMD-style instructions, varying levels of features. We have ARM Neon in alphabetical order, no preference here. ARM Neon, Intel AVX, Power, and Spark. Spark was been around for a while, I think. It was in the early stage used for image processing and stuff like that. So that may have been an early mover, but it really hasn't advanced as far as some of the others have nowadays. And then there are coprocessors like the Spark Data Analytics Accelerator DAX that was mentioned by John Fowler in one of the keynotes in Oracle Open World. And then they have a Java API, Stream-like API that can call into this coprocessor. This is one of the use cases we're looking at in terms of investigating for our APIs. Is can we leverage SIMD instructions, but also can we leverage coprocessors like the Spark DAX? Moving on a bit more general, we have these guys like GPUs and FPGAs. These are a little harder, tougher nut to crack more generally, but I think for constrained data problems, we could probably work out how to better leverage these types of things in the future too, with a bit more of research, I think. Project Sumatra is an open JDK project which has tried to leverage Java on the GPUs more generally. That is a much harder problem and potentially restricting your problem to more data-oriented processing. So here's a really, really simple example, SIMD example, 32 bits, arrays of floats. Say I wanted to add float A, the elements in float array A and float array B and put them into results. So normally what you do is you write a for loop in Java, you'd stride through it one by one by one, and adding each one at a time, striding through one lane at a time. If you're going to use 64 bits, like say a long, you could do it 2 lanes at a time and do 4 less instructions. But you can go one level higher, you can do 128 bits at a time and do 2 instructions, or you can take it even further, 256, and do it in 1 instruction like that. So that's the general concept. So there's 8 lanes you can do in one go in 1 instruction. You can go even to 5112 bits on Intel AVX, and I think that, I don't know whether that's a limit or not, but that hits your cache line sizes, which is sort of a nice value. I don't know if we'll get ever beyond that or whether it ever be advantageous to do so. So what have we got today in Java and SIMD? So Hotspot supports some of Intel's AVX instructions with help from Intel core engineers. They've been leveraging them into Hotspot, but only some of them are used. If you ever looked at the smorgasbord of AVX instructions out there, there is an enormous set of them. It's a very rich ISA, if you like, and there's lots of things to choose from. We're only using a small amount at the moment. There are superword optimizations in Hotspot C2 compiler, and they will derive SIMD code from sequential code, like a normal for loop. And these can work quite well in some cases. And then we have specific intrinsics for array copying, filling, and comparison. We've been working with Intel on doing leveraging AVX instructions for these types of things. The latest one we added was a lexicographical array comparison, and we intrinsify the array comparison. That's important because people were using a class called sunmisc unsafe for that previously, and that didn't work in all platforms. A little more on that today. So what do? They roll your own. Some people roll their own today with 64-bit operations. You can use something called the var handle array views, which I talked about in previous JVMLS sessions and a little bit at Java 1 last year. Or you can use unsafe get put long. How many people have used unsafe get put long to try and squeeze out an extra mileage from your data? That is dangerous. But people do it, and you've got to know what you're doing. And then people use JNI. How many people have used JNI to sort of get special access to your data, going off heap and making sure everything's nicely aligned? So if you use JNI, to overcome the cost of JNI, often you might use larger data sets and ensure that your marshalling costs between the boundary of Java and native is low to ameliorate the invocation costs of JNI itself, which can be expensive. So some of the problems here, superword optimizations can be quite brittle. If you write your for loops just right, it's really good. But if you slightly go outside the way that indexing occurs and stuff like that, your performance can drop off the cliff. So you have to know what you're doing. Intrinsics or point fixes are not general, and it's often quite expensive to add a specific intrinsic, at least a hotspot. Rolling your own in Java is limited and might not be portable. You might have a byte odor issue, is what John Rose calls it. You might have an endian problem, or an unaligned problem, or both, and it might not be portable. For example, Apache, the classic canonical example is Apache, Lucene, Hadoop, leveraging lexicographical array comparison using unsafe. That's great. It works well on x86 because it works on unaligned access, but for Spark, boom, it can crash or really slow down. So you're not necessarily writing portable code, which you would like to do for people using Java. It's an understatement to say that JNI is hard to develop and maintain. That's what Project Panama will help solve. I'll talk a little bit about later. So the motivation is we want better Java support for crunching on data. We want to really improve that use case. And that's data for it's regularly laid out in memory in a predictable pattern. And so this is for big data applications like Apache Flink, Apache Spark. They currently use unsafe and JNI, or they even use an interesting library called netlibjava. That's essentially a JNI wrapper around linear algebra packages or eigenvalue calculating packages and so forth like that. So I think Apache Spark or Flink might use these libraries there for that. This is an interesting use case for Project Panama as well. And as I was reading up on machine learning applications, that seems to be one of the hot things. If you're not into microservices, you might be into these instead. And apparently, in some cases, 8-bit precision can be good enough when you're doing some of these calculations. That was a surprise to me. So it might mean that SIMD operations on bytes might be coming back into fashion rather than operating on floats. We'll see where that goes, but that's an interesting case for GPUs, where GPUs have traditionally crunched on red, green, blue data, which is all 8-bit stuff. So we'll see where that goes. So this is part of a bigger picture. It's part of Project Panama. which is all about moving Java closer to the metal, better, safer JNI. And it's also about Project Valhalla, as we'll see later on in more detail, about bringing value types to the Java platform. So I can have an int represented in list int, so generics over values, points represented as values which contain coordinates and so forth like that. And these are really interrelated because Panama would like to use value types itself, and Project Valhalla would like to use very nice, efficient layouts for arrays of value types. So we can get nice, good crunching on that data. So they actually overlap, but they also do separate bits. And there's really, I think, a bright future for the Java platform here. I've never seen it so good looking forward, and the effort and research done to move the Java platform forward in these two efforts. So we're going to talk about two design approaches. One is a lower level vector API and its implementation that encodes specifically whips into the API. And one is a higher level API, which is vector-based in its implementation. And we will be deriving Java bytecode from runtime compilation of expressions of a computation instead. So one is low, and then we're upping it so we can do more things underneath the covers and use compiler techniques to optimize even further. So both are general solutions. We're trying to be more general here. What we don't want to do is add point fixes to the platform, such as Dart's explicit types or Mozilla's SIMD basic types. You see these in the JavaScript APIs. There were bugs open. People logged into the JDK for adding types like this, and we closed them down. I find this unsatisfactory to add a bunch of types here. We have an explosion of types because someone probably I want my byte times 64 or something like that. And this, so we think we can do better than this. So what we're going to do is we're going to layer these approaches, and each is going to be built on the foundations of some basic value-based types and some what we call code snippets. And these will essentially define operations on registers and memory for certain bit sizes. Just check my time. Oh, I forgot to set the stopwatch. Okay, we'll see. Can you tell me a little bit when time is up? Okay. So here are some value-based types we've added to Project Panama, or more specifically, Vladimir added to Project Panama. We have long 2 for 128 bits, long 4 for 256, and long 8 for 5112. And these are currently value-based types. They're essentially boxes around fields of longs. We want them to be boxes without identity. So Hotspot can treat them specially. So I don't care about identity. I can optimize these better. And basically, we want to improve the escape analysis of these types of classes. So if we allocate them, the compiler can remove the allocation. So I don't need the allocation. I just want what's underneath. And I want to map what's underneath to a register in the CPU. And these things are essentially views over packed values, as we'll see later on. What we want to do is extract values from arrays and put them back to arrays. So code snippets, the mantra I have, which is not quite accurate, but I think gets the point across, is that it codes like a Java expression and works like a hotspot intrinsic. You can think of it like that. What we want to do, this is an experiment to lower the barrier or make it easier for us to experiment further with vector-style computations. If we had to do this at the hotspot level in C++, this would be hard work. So we want to speed up our innovation here. So the idea is we wrap a few machine code instructions with a specified calling convention in a method handle, so we can easily wrap a few AVX instructions, 1, 2, 3, a little packet of machine code. So it's very platform specific, very easy, unsafe mechanism to jump into a bit of machine code. So here is a slightly curated example. We'll link to source code later on. You will see examples like this in the source code, but this is slightly curated. So what we have here is a little factory to make a code snippet, and it's essentially calling a specific instruction to add 2 YMM registers in AVX. So that's essentially the floats I showed you earlier, 4 floats in one go we want to add together and return the result, 4 lane-wise. Like so. Is it 4 or 8? It's 8 lane-wise. Yes, 8 lane-wise, because it's 256 bits. So what we define is the method type. So we're using these value type classes we referred to before. We have a method type here. It returns a long for and accepts as arguments one long for we want to add and the other long for we want to add, like so. So we don't effectively, we say we require AVX2 because this instruction is AVX2 only. And then we define the register, say I put question mark here because we're not going to hard code what the specific registers are here. This is something we do later on because there might be a calling convention described in this little packet and each platform may have a different calling convention we need to map to. And this is how it might look like in code. So we have float arrays, A, B, and C. At a specific index, we might want to extract the long for value at a specific index, extract out 8 floats into this long for value. We might want to extract another one from B, and then we want to add them together by calling invoke exact on the method handle. And this is where the instruction will be called. And then we want to apply it back to the array. That's the basic essence of it. Yes, very much so. So you'd have to, for each platform, you'd have to provide separate code snippets for it to work. When you up the level of the API, it's where you can monkey around under the covers for each platform using this same technique. So code snippets are bound for a method handle, invoke throws exceptions we want to catch. So arguments are unchecked, but we check the types of the long fors and so forth like that. And there are a bunch of examples we have in a class called patchable vector utils. And essentially, we need to provide factories for different platforms, and we'll work that out. So here's a specific example in code you can see from patchable vector utils. We want to load from a float array 2 long for values, and then we want to add them up, and then we want to put them back. So that's essentially what I described earlier in code. And each of these encapsulates the method handle invocation to code snippets. And this is what essentially the assembler looks like. If we print out the generated method from C2, we essentially see we got a load from memory here. We've got another load. We're adding them together, and then we're storing them back. So it's very, very tight. You get exactly what you want here coming out into C2. Very precise. So here's another example. Notice that in the previous example, we were doing 2 explicit loads from the array. To get the point across that code snippets are very precise. Well, this is creating 2 instructions. Well, perhaps I can load directly from memory instead of doing two loads from memory. I can use the add method and load one, use one from a register and use one from a memory address instead. So we can even slightly change it, have a different method for add that takes in the array and the index for write instead of 2 values. And then we only get 1 load instruction, if you can see it there. And then we add from memory and 1 register. We can even compress that down. We're dealing really low-level things here. And this may or may not map to different CPUs. Okay, I think I'm done. I'm going to hand over to Ian. Okay.
All right. Start my timer here. Okay. Just to dovetail on the previous remarks about these assembly, these are actually dumped from print assembly from C2. These aren't abridged in any way, so this is actually what is coming out for the add arrays methods. So pretty much all of the assembly in this talk that we present has been presented either in a way that's true to form, has only been let's say abridged again just for readability's sake, but is true to how it actually appears from print assembly. And I encourage you to check out the Panama source code and try it yourself sometime. So anyway, to go in a little more depth, we decided to do matrix multiplication with SGEM. So SGEM is a pretty common matrix multiplication algorithm seen in LibBLOS, 32-bit floating point matrix multiplication. We take a naive approach that everybody who's been in a CS class or has read an algorithms book has probably seen before going on to a more sophisticated approach, plus a couple cache efficiency tweaks, doing row major reordering, or I should say column major reordering in one of the arrays, just typical basic stuff. We have a baseline version that's modestly optimized in ways that you would write it in Java, and then some vectorized versions that are a bit more aggressively hand optimized. So your scalar matrix multiplication is right here with some additional hoisting to save you on some cycles here and here. There's not a whole lot to it. With BLOS, you have some scaling with alpha and beta variables that come in. You do your matrix multiplication, and you pipe them out to a resulting C matrix. It's not any more complicated than that. So stepping forward into patchable vecutils and using some of our intrinsics, we just tweak the kernel a little bit with our vector primitives. Notice that we're now stepping by 8, because this is the length of our long 4 in terms of float 32. And then we do our multiplication, as well as extracting. We multiply with our scaling. This is another sunk load trick, as well as loading another guy out. And then we have a macro instruction that we've encoded in code snippets. So code snippets leading up to this point have been primarily single instruction intrinsics, but you're not limited to single instructions. You can encode macro style instructions. So in this case, this is a dot product intrinsic that I sort of will gloss over and hand wave. Another thing I've left out of this specific example is in the prior one, we scale by beta inside our kernel. In this one, we scale by beta in advance using vector primitives. It's not exactly, I think you can get into a bit of a philosophical discussion with what exactly is apples to apples in this comparison, but you could, in theory, probably take beta out of this loop and pre-scale it in a loop if you know that superword will optimize that loop and vectorize it. But you're getting into kind of this strange territory when you start writing optimized scalar code like that, intending for vector optimizations to take hold. So just for the sake of this example and for some basic perf analysis, I left that out and did it this way. So to make things a little more fun, walking up out of the data parallel region into a thread parallel region, you can take streams and just hoist your kernel right in there and do it in streams parallel. So matrix multiplication falls into one of those embarrassingly parallel types of problems. As long as you're not reading from the matrix that you're writing to, and in this case, let's just assume that for presentation's sake, all you have to do is take the outer loop, the I loop, and replace it with an int stream, which is just an inductive step, and attach parallel and do a for each in the middle, and boom, now you're leveraging all your cores. So I would like to say that I could definitively give you the performance estimates of doing it this way. I have, again, I encourage you to run it yourself. I've seen some pretty wild numbers come out of this, so I'm not in a comfortable position to really share share those yet. But Panama is very much a work in progress, so we'll just stick with the numbers that we have for comparing our baseline with superword versus our vectorization techniques. So basically with performance estimates, these will be checked into Panama. Some of these, the harness for this I think has been checked into Panama. I have to push up the actual code examples from this talk. Standard micro benchmark fare, use JMH. I ran it on an Intel 6700K, just my desktop. Default C2 configuration, so no disabling loop unrolling, no disabling superword. Just to try to be fair. So note the red, it's highly preliminary, don't hold me to this, don't come find me later if it doesn't pan out for you quite the same way. Be nice. But so as there'll be more precise analysis to come as we're still trying to figure out the nature of using fork join in this area. So I leave the multi-threaded analysis to the reader. So just a relative speed up. And this will be this example versus this example. Base example with standard C2 optimization fare on an x86 6700. Square matrices assumed in the x-axis. So you get about a 1.5 baseline speed up, which picks up to about nearly 3.5 at around 512, 1024, and that's when you've saturated your level 3 cache on the entire processor, so you'll see degradation falling off after that. We note that there is also a missing test in here because 128 has some problems, just the size 128. So very much still a work in progress, but we're fairly confident that these numbers are fairly stable. We've run them a number of times. So what this basically shows is that just using vector primitives will get you speed up over the standard fare optimizations for a naive matrix multiplication implementation. So when you graduate to even more embarrassingly parallel problems that spend a lot more time in the vector space, where a compiler probably would not be able to follow you with optimization so closely, as I'll show an example later on, you'll see a lot more of a speed up. So basically, the longer you can spend in the vector space, the more oomph you're going to get out of these instructions. So we mentioned code snippets, and if you notice, code snippets, the way they're implemented is you give the Java compiler literal bytes, and you say, hey, inline that, and don't ask me any more questions, and try to run that. So from a security angle, there's some questions regarding that API, but I think the general understanding at this point is that we will probably not be exposing maybe that API to the pub.
It's hard to say. It's essentially an unsafe API.
Yes, yes. So we eschew unsafe, but then we do code snippets. So code snippets should probably be viewed mostly as an implementer's tool, which you can use yourself right now in Panama. But with the advent of Jigsaw and the module system, it will probably be, or some equivalent form will be hidden away deep inside the bowels of the JVM where people can't get to it, or however that will work. So the vector API is kind of the next layer of abstraction that lives on top of code snippets that kind of exists in more or less a one-to-one correspondence with code snippets, invocations, and instructions. So data parallel operations over size types, and we're getting over code snippets. Wrapping them up, this draft I think Paul mentioned. Paul snuck it into his talk last year. This draft was proposed by John Rose, the VM architect, in 2015. There are a number of different prototype implementations living in Panama that you can check out. And the base type is just vector. So you see this here, it's just vector ES, where S is a shape. Shape is the vector size, which is a bitwise size, and this is primarily for correspondence to register classes. So you'll have a 64-bit register, a 128-bit register. This isn't set in stone. We have, I think, had some back and forth conversations on whether or not it should be vector length, so element length. But in this case, we're sticking to bitwise length. So the element type E is just your int, your float, your double. So in the case of AVX, and your mileage is going to vary based on what ISA you're operating on in the real world, but broad support generally is seen for int, float, and double. Again, there's some variation there, but we kind of have been centering around those types. So a small example with the vector API. So it's kind of similar to what you've seen before, but this is an add arrays with the vector API, left, right, and a result. You have a float vector. And this is actually a specialized vector. So before I mentioned we have vector ES. In this example, it is float vector, which is you could consider it akin to an int stream or a double stream. We've gone both ways with this. The issue with vector, I'll just address this now. So without the presence of value type specialization, E implies a box type, and if you're parameterizing it to array and from array by an element type E, you'll end up asking for big float array or into big float array, which are kind of pathological arrays that people wag their finger at you for using. So float vector is a workaround for this right now. So essentially, you just say, we declare our float vectors, we unmarshal them from the array in a similar manner that we've seen before, and then we add them together, and then we pipe them back out into the array. It's basic stuff, and so add arrays is kind of like a binary reduction of two arrays with our workload doing this over an index. Nothing too exciting, but just a general gist for how it works. Yes? Say it one more time.
This is supposed to be generic, not platform dependent. So why would I like to make this explicit for length? Because maybe my platform only supports 120.
Right. So yes. So the question is, it should be more generic than just platform independence. Yes. Yes, and the next example is. So yes. No, that's a very good catch, though. This is a very specific example set to 256, 256 bit registers. But we can actually parameterize and sort of loosen up the constraint on the shape. So yes, this is just really specific and a very tight example. If your platform didn't support 256, this would break. So even with the vector API, there is this risk of over-specifying and then becoming incompatible when you play with the shape at all. And to some extent, even playing with the element type on certain platforms may preclude the use of certain mathematical operations or arithmetic operations. So this has really been kind of a spelunking attempt into figuring out what is the broadest core collection of operations that we can broadcast across the most platforms. Additionally, there may even be some work to investigate whether or not, like, maybe even query what you can do on certain platforms, because there are graduated operations in complexity. There's your base, add, subtract, etc. But then there are some more bitwise, fancier operations that could be available on certain platforms, but not others. How do you, if you know you have it, how do you figure out that it's there without sort of sacrificing the genericity of your code? All open questions. So the vector API, as it's defined, they're like these basic operations parameterized by ENS. So your adds, your moles, and your logical operations. And then we kind of step from those into intermediate operations. So marshalling and unmarshalling, getting elements out, putting elements in. At this point, we're still constrained by the boxing, but the cost for individual things isn't so bad in the presence of auto-boxing necessarily. There's a lot of caveats here. Working on it. And so putting elements in. And then you can notice there are also some summalls, horizontal reductions. Those would be kind of platform specific. In the case of things like floats, the order of operation in your reductions matter. So the implementation has to be explicit to a particular reduction. Will you reduce straightwise left to right? Or if you do it a different way, how do you make that way explicit? Or do we care that much? All open questions still. So then arrives more advanced operations that are in the spec. And these come with their own issues. And if you're raising your eyebrows to this, you're probably on track. So you have your maps, you have higher order functions, taking in lambdas that are parameterized by the scalar element type of the vector. So how does that work? Well, we'll get there, maybe. So these are sort of the fully realized expressiveness of the vector API, where I can tell you right now it would be very nice to have them, but at this point they may not live onward into the resultant spec. They will be realized in a different fashion. So before I go any further, I will tab out and show you a quick example with more generic style here. So there's a Mandelbrot example based on an example from GitHub. Let me close that. See if my Windows powers are good enough to. Okay, and then we are mirrored. Okay, so the Mandelbrot example is based on an example this guy named Guido on Twitter wrote. He has a number of implementations in this repository. I think we found this is more of a point of interest. This is a Mandelbrot implementation based on Intel intrinsics, if you're familiar with them. There are also a number of other ones based on other ISAs. Fairly straightforward. I can't comment too closely on this because basically all I did here was a direct transformation using the vector API. So the equivalent vector API code looks very similar. Now, like what we were saying earlier, in this case, what we're starting from is we can create sort of a template or a more loose definition for vectors without regards for their shape. But what this requires us to do is at some point pass in an object that bears that information that we're going to carry forward through the computation. And this is just one way to do it right now. So essentially, we have broadcasting up here, at least on x86, we call it broadcasting. So from elements, we're broadcasting elements across the vector. We have using a little lambdas to get around some C-isms right in here. But essentially, it's still, using the vector API, at least versus Intel Intrinsics, is a fairly straightforward one-to-one transformation. That said, there are other ICEs out there, and so we are wary of overfitting for a particular ISA. However, this is still fairly generic at this point.
So in this would be a safe API. So you shouldn't be crashing. It does at the moment sometimes, but that's because Hotspot isn't optimized properly. More talk, but this is a safe API, and if some platform doesn't support it, it would have to support it in Java instead and emulate the functionality. So that it would keep on running or keep on trucking, but it may not be as optimal on all platforms.
Right, right. And I think another thing to consider here that we've had some conversations about is that what does degradation look like when you are missing the necessary platform functionality to support this operation? How do you fall back? Do you fall back to, if you don't have 256, do you double down on 128? What kind of, sometimes people value performance at the utmost, or they want consistency. They want consistency in their behavior as well, so that can matter as well. So these are all conversations that are ongoing. This is still very early work, but yeah, so degradation is sort of unaddressed at this point because we're really focused on getting it to work at all. But we've had some pretty good results with this. So well, you can see my next slide. Let me go back to extended. And then there. Okay. And so the result out of this vector API implementation is a Mandelbrot. I mean, it looks fairly Mandelbrot-y to everybody who's seen one before. So the performance of the vector API, right? Paul noted earlier there's boxing involved in the extended value types. The vector API right now suffers from boxing. It's a work in progress. It depends, the performance for the vector API depends heavily right now upon escape analysis functioning correctly. So whenever you have a vector API object returning another vector API object, it's implicit that there's an aspect of immutability happening there, which deep in my own brain, I sort of assume that to mean that new is being uttered somewhere in this process if everything's boxed under a fresh object. So getting around that with escape analysis is kind of an interesting place because it puts us in this optimizations as semantics realm where, oh, well, if the optimization works, then what we really mean is this is all going to be on the stack and it's going to be great. Ultimately, what we hope to see is value types solving this problem for us. That is the ultimate solution. It's possible we could see a vector API surface before value types, but a full-blown vector API will be concurrent with the arrival of value types. So as you can see here, vector float s, well, that's no great. Not great, no good. I speak good. Float vector extends vector float, so trying to play the stream game. Also undesirable. We end up in a place where streams is now, which I think is suboptimal and unsatisfying. But finally, where we'd really like to get is vectors just parameterized by the primitive types. So value types to the rescue, like we said. Project Valhalla and Project Panama are different projects, but there are a lot of implicit dependencies that are emerging between the two. I think it was about a month ago, a smaller sort of rough cuts implementation for value types for implementers like us was proposed by John Rose. I don't know if you really want to comment on how that impacts any kind of timeline.
It's got shady value types.
Yes, shady value types.
Value types in the shade. Trying to put them in, not in the language, but first in the VM and in the bytecode. And then you can code them through method handles might be a way to get these in sooner so that people can experiment with them. And then we build up layer on top, the real generics over values later on. So this may be of interest to us. And I think Vladimir's heroic work in escape analysis in C2 will feed into this in some way. I think it's good experience.
Thank you very much, Vladimir.
Yeah.
We know you're watching right now. So getting the code snippet types completely out of the box and getting vectors out of the box. But yes, the timeline's open on that.
Just not Java 9.
Just not Java 9. Yeah, that bums me out, but c'est la vie. I wanted to say the other thing about shady value types was that it would be value types without, I think the proposal was value types without any syntactic Java impacts on Java syntactically. It would all be JVM, deep JVM type optimizations.
Method handles.
Yes. Everything would be under method handles, which is consistent with what we're doing so far. So, all right, to step into the final leg of this talk, which the propeller hats come out a little bit. Remember those advanced features that I said, don't think too hard about these advanced features in this current iteration? So, map. Take map, for example. You have a binary reduction. You want to map a binary operator over two different vectors and reduce them. The inbound lambdas are scalar defined over the element type E. Okay? So if you get a lambda, if I'm running at runtime and somebody hands me a lambda and I'm a vectorizer, but I have this lambda, which is bytecode that could contain Lord knows what, and I try to convert that into a vectorizable form, I'm probably going to fail most of the time. Also, doing that in general would imply something like trying to crack open the bytecode of a serialized lambda and then reinterpret it in an abstract form. And we don't want to go there. Not to mention lambdas are Turing tarpets anyway, so you could have a whole world in a lambda. So we want to constrain this down and make it work. So the expression language is sort of an offered up solution to this problem that we're also experimenting with. So like I said at the bottom, we don't have a good way to reify lambdas. C# has expression trees. Java doesn't have that. That seems like, a bit too big of a solution just to solve this one problem. So how to inspect a lambda? So how about we just put an AST, like an explicit AST, inside of a lambda? Okay, but we use a regular lambda so we can still compose things. Okay, maybe. Just roll with me for a little bit. We base it on code snippets in the method handle API, and when you're coding, you think of coding inside the lane, meaning vectors have lanes of elements. So when you're coding, you're focusing on one lane going through, flowing through a piece of computation, kind of a stream-like way or something. So this follows from this series of thoughts. Say, vector operations are simple expressions. Okay, maybe so. Expressions are trees parameterized by an element type. Okay, method handles, which we've discussed a bit, can be combined in the tree-like way. Just as a show of hands, who all here is familiar with method handles? Okay, a little bit. All right, who else? Okay, say method handle. Who else familiar with method handles, the library, the combinator library? These guys are. Okay, that's okay. Basically, what I'm getting at is there exists a library to take existing method handles and combine them and then map their inputs and outputs to each other. It's very functional in a way, and we can use this with the vector API intrinsics. So say you have a function up here. Oh goodness, I touched it without my laser pointer. Function, goodness. Right, there we go. Okay, never mind, I'm not gonna do it. Laser pointer, right here. Okay, so see this right here. Say we have a lambda we want to implement, but we want to do it with method handles, and we want to do it in a vectorized form. So we take these two, we specify our method type, and then we instantiate our code snippets, and then we use collect arguments to merge these guys together. So one guy gets the result of the other guy, and then what you end up is with a machine where you want two inputs, and the inputs map down, kind of like the next slide. So so basically what this point illustrates is you can by hand take an expression that you see and then use the method handles combinator library to recompose that expression with vectorized baseline functions. So instead of doing it by hand every time, what if you start with an AST? So you start with an AST that is just a single expression, kind of a templated form. And so say XY points to some expression tree, and we have an AST visitor that walks that expression tree, and then when it sees an add, it uses vadd_ps. When it sees a mul, it uses vmul_ps, and then it takes the method handles library and ties it all back together in a nice, tidy way. So it behooves us to establish an expression language with a kind of in an Edsel style domain-specific language in Java. It's a little clunky, but so we have this interface here with our nodes that we're interested in, and we compose those together. For reductions, we libraryize our reductions, and this is just sort of a working example. So we libraryize these reductions. Say you have a binary reduction, as before, like with add arrays, but in this case, what we're defining in our workload, our loop kernel that we want to customize a loop with, we say left, right, dest with our arrays, and then we have our loop body, LR, and we have an expression. We do add mul, like we did before, but this is all in data in Java. What we get back is a method handle, and then we invoke that method handle. And I'm not lying to you, this is the assembly that C2 spits out. So right now, what you get is the loads, the adds, and the muls, and then the loop stuff here, and then there you go. So this is basically what you get. So you end up in a really nice place with regards to code gen. So the applications of the expression tree is you can vectorize without thinking about individual vectors on the vector level, or superword for that matter. So you're not thinking about programming for the optimizations. It's a higher order flavor of programming. It works in this case. You can focus on loop kernels. So there's some trade-offs to this, though. Control flow is hard to get right. Another thing is when you're using lambdas as templates, and inside of your lambda body you were to say, you were to put in conditionals, you were to put in anything that was not within the language of the Edsel, that only gets fired off once. Really what you're doing is you're trying to construct syntax trees, so that kind of starts to break down this natural, it doesn't feel natural for larger examples. We can get conditionals in the expression language, but they come at a trade-off. If you have deep branching, what you're usually going to say on a lot of ISAs is you're going to mask your operations, and so you have to do double work and mask for each branch that you're masking for. You're going to have to execute both branches with the correct masks in place. So still more thought to be put on that one. And we don't have vector level operations, and there are interesting vector level operations, so blending and shuffling of vectors. And like I said before, these aren't regular lambdas. We do put in some debugging that allows you to, so peak in stream. You can put a peak in this expression tree, but that will also come at a risk for major performance hit. But I mean, when you're debugging, it's kind of understood, at least when you're prototyping a vector API anyway. So the last thing being is when you do this declarative style, you have to develop this sort of implicit trust for the compiler. Some people are okay with that. I think folks in the functional realm are a bit more okay with that, but folks who prefer an imperative kind of near the metal kind of programming, it's less comfortable. So, it depends on if it's your flavor or not. So, basically to sum it up, a vector API makes sense in Java. We can come up with different complementary APIs, very much prototypes. But so far, so good. We see decent perf characteristics emerging out of these prototypes with a lot more work to do. But we see some speed ups and versus the baseline being optimized by the compiler. That's good. It's sort of a nice sanity check, so I think we're headed in the right direction. So continuing work, enhancing the baseline API. As far as the expression language is concerned, we are interested in somehow finding a dovetail between the two where it makes sense to do one or the other attached to vectors. Higher order functionality is great. Java is going there. It's nice to live where everybody else is, but we can't let that hold us back too much. So I think the vector API is sort of a priority with the expression languages kind of riding closely behind it. And then lastly, we want to synergize with all the nice JVM features that are on the horizon that we hear so much about and we're so anxious to get our hands on, specifically value types. Can't say that word enough. I feel like once we have value types is a phrase that we say so much. Once we have value types, we can all retire on the beach and be done. So anyway, if you're interested, it's in the Panama project. I know that saying it's in the Panama project is like finding a needle in the haystack. So the JDK test Panama Vector API patchable it's in there. There's additional codes. I think there's some code samples from here that may not be up there in the current form, so I will check those in. There's some Maven build scripts in there, so you can get started. Still very, very prototype. I can't underscore that enough. Some legalese right there, and then another caveat is that right now these prototypes build on Unix systems. A lot of Panama and a lot of the vector API depends on the presence of System 5 AMD64 ABIs to be in place. We haven't gotten around to Windows yet, hence me presenting on a Windows machine and showing you code that ran earlier. Windows is a work in progress. If somebody wants to come on and implement that, that'd be great. No, that guy's shaking his head. No, okay, fine. So anyway, it's all a work in progress, and we all love to have more company. So I think that wraps it up. Okay. Are there any questions? Yeah.
So how is it supposed to work if you have this general version, not a specialized one, which shows you just specify a vector without specifying the layout? Would the specialization happen in Java code, or will this all be done by the JIT compiler? I mean, the way down to the code snippets, which are then that specific. I mean, if you do this in Java, you will need actually a compiler in Java which matches then the best implementation. And you would have to do the same thing which is done in C2 in Java to get the optimal solution.
Are you just so are you talking about the Mandelbrot code, or are you talking about the vector code, the vector API?
Yeah.
Okay. The selection, so you can think of it, so the question I guess is, where are the instruction selection done, essentially? Is it done in Java or is it done in C2? And the answer is both at this point. So what's happening in that example is, for better or for worse, we're supplying a vector object singleton that has the functions that you're going to use, and then that rides through the templated computation that we laid out.
But you have only one implementation now. I mean, the question is if you have several.
Yeah,
Several backends.
right.
One supports 128, one 200.
So I would say that I can't comment on, I can't say definitively how that would look for the vector API, because the current state of the vector API is generating code with the boxing that makes that especially difficult to predict.
I think what you'd have is a sort of factory level API, and you'd split out the implementations in the source code base according to the style we have in OpenJDK or something like that. So when you build a JDK for PowerPC or build a JDK for Intel, it would slot in the right implementations into the released image. So that's how, so it would go down to the right code snippets underneath the covers for the right platform, but the API up top wouldn't change. So it's a design question to be decided. I call this an implementation detail. It's purely just a coding matter. I'm not trivializing it. It's a problem we need to solve, but I don't think it's a hard problem. We need a terribly hard problem. It's just.
It's an interesting approach, but this would mean you would have different runtime jars on PowerPC and on.
Yep. There's already a difference in terms of, say, Windows. There's some subtle differences in the code bases already in the OpenJDK. So it's doing that more in the extreme than we've seen before. Essentially, the Mac has very different implementation for some of the rendering of swing and stuff like that, I think. So it's not unusual. Pardon? Some of them. Yes. Yes. Yeah, to repeat the observation, the Java Neo APIs also behave slightly like that. So we're looking at code snippets as a way to make progress fast on this. It's something that's an experimental trick at the moment, or experimental technique to make progress in this area. And it may be something that stays there and sediments down as a toolkit for us to use to progress forward in this manner. And for others like yourself, and for people on ARM to try this on their own and see how this works out.
But I mean, even if you're on Intel,
Yes, that's why we had the code snippet saying require AVX2. Yes, it's a problem. So we need to segment this out based on support. So it's a problem that C2 already has, and we're going to emulate some of that in Java to restrict the functionality on different platforms.
Exactly the question. So you need to choose at runtime when you execute this. You need
Yes, there's some runtime things. You're right. Yes, there's some runtime aspects which we can code in as constants. We can static final fields we can set just once at runtime based on the characteristics. So I don't think there's going to be a performance issue with regards to that. But it's working out the set of things that are supported and having the separate implementations do that. So it's going to be an implementation design challenge to get the best way to structure that.
Have you started on the GPUs yet? Specifically, what are your thoughts about the streaming of data back and forth?
Can you repeat the question?
Yeah, a little louder.
Sorry.
Yeah.
Have you thought about GPUs yet, and what have you specifically done regarding streaming of data back and forth to GPU?
So have we thought about GPUs yet and streaming the data back and forth? So the overhead there involved in that? I have
No.
not. No.
Project Sumatra has in the more general form, and they were trying to do Java streams, and one of the problems they encountered was exactly that. Major hits. So that's one of the problems with the GPUs, and that's why I also talked about the Solaris DAX data accelerator. It's specifically streaming based. It was originally designed to optimize PL SQL, but it's very simple kinds of operations you can describe, and you basically pointed at array references or stuff like that, and it shares the same memory as the CPU itself in terms of access, and it's a much easier problem to solve going to something like that than it is to a GPU. Hard problem.
Yeah, I think that's a really important question, though. We've been focusing on vectors as you would see them in traditional CPU SIMD, but heterogeneous architectures are blowing up right now. It's kind of an understatement, and coming up with a programming model that is far enough removed that it can live across most of those is pretty challenging. But it's something we're considering. I think thinking about your computations at more of a high expression level and maybe abstracting control flow or conditionals out a little farther can get you some mileage in that area. But when you start thinking about the overhead, I mean, with GPUs or even FPGAs or anything like that, there's all these little really platform-specific latency characteristics, memory shuffling characteristics that you really have to start to think about. And smoke's coming out of my ears.
It's a hard problem. Using this expression language at the moment where it's designed, this is a level we want to get to so we can start trying to do those forms of experiments. Because the higher the level, the more you can monkey around under the covers of all sorts of things. An interesting point, what if we could make that expression language more Java-like in terms of syntax going forward? Mm-hmm. What if we could stuff that in as an AST inside, as a side to the bytecode? And what if the compiler could crunch on that extra information? So there's all these high-level thoughts we're having about all this going forward. So it's like an extra compilation step in there. And I think interesting research project.
One thing about your chosen solution
Mm-hmm.
is the fact, or I should say your chosen platform, is the fact that currently Intel has a lock on AWS, Google, and Azure on all of their hardware.
Can you repeat that?
So you noted that AWS, Google,
and
Azure,
all of their hardware is Intel, 100%.
That's your observation. That's an area. Yes. I'm not disagreeing with you. However,
Feel free to double check on their own documentation.
No, I trust you. Yeah.
Well, this means that what they're doing will run on the cloud, or at least on the major cloud providers, as is, once they've got it working.
Big if, right? I said once we've got it working. Yeah, that's the catchphrase there.
But just to summarize, because there's a bit of a question and answer in the audience. So Basically, most people run on x86, and most cloud vendors run on x86. So you're targeting the biggest audience essentially. And I think a lot of libraries actually assume that at the moment in terms of performance. Apache, Hadoop, and Lucene mostly compile best in x86. We're finding that we're doing a lot of work to try and make Spark better for these platforms.
There's two x86 implementations. AMD has one as well, and in certain areas, their hardware actually performs better than the Intel, but it's only on certain areas.
Okay, so to summarize, AMD does slightly better in some areas, but not in others. Okay. Okay, I think we're out of time. Thank you so much for attending.
Thanks.